This is example 2 of a dependent samples t-test, and it follows up on chapter 11 part 3. This is where it ended. In this problem, students are given a test of statistical knowledge before and after a section of class. Did the students increase their knowledge? Do the hypothesis test with a significance level of 0.05. So for this problem, a couple things to pay attention to right off the bat is we're looking for an increase of knowledge, and the level of significance is 0.05. So I want to highlight, right, to increase their knowledge. We got to remember that when we calculate the difference, and that will lead to a very interesting situation down the road. But basically, this is a repeated measures test. It's one set of students. They're tested before and after a section of class. So according to the null hypothesis, before equals after. There would be no difference between these two measurements. The null hypothesis says that they did not increase their knowledge. So if we have the difference as a score XB at any person's before score minus their after score, we should then expect differences of 0. According to the alternative hypothesis, well, increasing their knowledge, well, if we've got this difference, right, XB minus XA, and this is the relationship, before less than after, they should increase their knowledge. They should know more about statistics afterwards. Then we would expect D scores less than 0, right? D scores less than 0. Now this is where it seems to not make sense. We're going to expect negative differences scores, right, when students are better afterwards. That seems to disagree with the word increase, right? With increase, you expect pluses. But the way this difference score is calculated is upside down. It makes it seem upside down. If we expect people to be afterwards, to increase their knowledge, then they're going to be better, have better scores here afterwards. So of course, we're going to get negative difference scores. This happens a lot with pre-post kinds of designs, is that the difference scores seem to tell you the opposite of what they really do. But in this situation, a negative difference score tells me that the students increased their knowledge. So the null hypothesis is going to be the population mean D equals 0. That's always going to be our null. The alternative is going to be mu D less than 0. Right? Because according to this belief, increasing their knowledge, and with this setup of the differences, I should see negative difference scores. So I would expect a mean difference to be something significantly less than 0. The second step of any hypothesis test is the rejection region. So for this problem, what do we need to know? Well, it's a t-test. So we need to know the sign from the alternative, which is a less than. So I know this is going to be a left-tailed test. Degrees of freedom for dependent samples is n-1. Here there's 6 participants. 6 minus 1 is 5. And the level of significance is 0.05. So the rejection region is going to look like this, a left-tailed test, and the critical value is negative 2.015. We're going to reject the null hypothesis. If we get a t-value less than negative, I'll write that out, t obtained less than or equal to negative 2.015. All right, so let's do the work for this test. And here's the scores themselves. And you can see how the students did. This first person scored a 75 before, a 95 afterwards. The second person, 85 before, 84 afterwards. So in calculating the difference scores, and you see the top row here, this is what we need to find. The differences defined B minus A before minus after. Then I'm going to get the deviations and then square the deviations. So for this test, in fact, you can be a good idea to copy these numbers down on a piece of paper and calculate these differences and try and stay a step ahead. So if you stop the playback now and do that work, you'll be able to check and see how you do once I reveal the answers. Okay, here's the difference scores. The first person is a minus 20. That tells me they scored 20 points higher afterwards because it's negative. The next difference score is 1. That tells me they scored 1 point higher before. And you see the rest of the different scores are negative. If you add up those different scores, you should get a negative 49. And then the mean difference is negative 49 divided by 6, which is a negative 8.17. There's my D bar. There's my mean difference. The next step is to calculate the deviations and then square each one. And once again, right, it's a good idea to try and get ahead of me. Try this yourself and see how it works out. Here's the first two. Right, minus 20 is the difference score for the first person. The mean is negative 8.17. Negative 20 minus negative 8.17 is 11.83. Remember that rule from grammar school. Subtracting a negative is like adding a positive. So that becomes negative 20 effectively plus 8.17, which is 11.83. The next one is a different score of 1. 1 minus negative 8.17 is 9.17. And then you see in the final column, I squared each of those different each of those deviations. There we go, right? There's the squares. Here's the deviation, square it, 139.05. 9.17 squared, 84.09. There's the rest of the deviations and their squared values. Now we do all this because we want to sum the deviations that have been squared, right? And this gives us the sums of squares, or right, we could say it's going to be sigma, put a sigma in front of that, the sum of the deviations that have been squared. So for this problem with a D bar that is negative 8.17, we get a sum of the squared deviations of 250.83. Let me just take a minute. I didn't talk about this, right? The D bar minus 8.17. What does that tell me? Right? It doesn't mean they did worse, even though it's negative. That tells me they actually did better afterwards. They seem to learn more, right? Because it's negative, says on average, people were 8.17 questions or points better afterwards than they were before. All right, so we've got the sums of squares of the difference. The next step is that we can calculate the standard deviation of the difference. The standard deviation of the difference, there's the formula. We take the sum that we just found, divide that by n minus 1, and take the square root. So filling in the numbers, there it is, just repeat it again, 250.83 is going to be the numerator, and n is 6, so 6 minus 1 goes in the denominator. Now I've got to solve all that. That's why I put the parentheses in before we do, before we take the square root. So that becomes 250.83 divided by 5, which becomes 50.17. And we take the square root of 50.17, and it is 7.08. So the standard deviation of the differences, S sub D, is 7.08. Now that we've done that, we can find the T. I don't know why it's doing that, sorry. Right? We found that the mean difference was 8.17, and we just found that the standard deviation of the difference was 7.08. So now we can fill in, we have everything we need to do the T. D bar, mu sub D, and then the stuff for the denominator. So if we fill them in, the mean difference is there, 8.17 minus 0. Remember, according to the null hypothesis, mu sub D equals 0. And then the denominator is where we figure the standard error, and we're doing this all in one step. So we take the standard deviation, 7.08, goes right there. The square root of n is underneath that. So taking this to the next step, we get negative 8.17 divided by the answer of 4.83 divided by 2.45. We do this division down here in the denominator, and it simplifies to negative 8.17 divided by 2.89, which is a negative 2.82. Negative 2.82 is the t obtained. Now we go to step 4, where we look back at the rejection region. There's the original problem. Students were given a test of statistical knowledge before and after a section of class. The students increased their knowledge, and we did the test with alpha 0.05. There's the rejection region. It was left-tailed because of the way we had the difference set up. And that was the critical value. We said we would reject the null hypothesis if we get a t obtained negative 2.015 or less. So what did we find? We found that t obtained was negative 2.82, which, I like to see this. There it is right there. It's going to be somewhere there, which is in the rejection region. So I will reject the null hypothesis and have evidence then that the students significantly increased in their knowledge as a result of the class.